can now start with the hardware of the control systems. I will introduce some case studies wherein the hardware used in the industrial sector will be introduced to you. Well, naturally we cannot go to a reasonable depth of discussion in terms of the hardware details, but the purpose will be their basic characteristics and how those characteristics affect a particular control system. That will be the basic objective of our discussion. I take up the first control system as a speed control system. This is the speed control system, and now you see how the system works and what are the basic ingredients in this particular system. In this particular case, you want to control the speed of the load. So, here is a load, the parameters are J and B. J and B are the parameters, the moment of inertia and the viscous friction B. Tw is the load torque on the system, that is, it is a disturbance torque acting on this particular system. Now, omega being the speed, so it means there is a specified omega, and you want the control system to act in such a way that this particular load runs at the specified value omega in spite of disturbances Tw acting on the system. This is the objective. So, in this case now, first of all, I need an actuator, the power device. In this particular case, the actuator, as you see, is a motor with a power amplifier. So, this power amplifier and the motor, they constitute an actuator for this particular load, because they provide the necessary torque for the load to run at the speed omega. Now, this particular actuator is getting the control signal U from a suitable controller. Here is the controller circuit, which in this particular case is a simple amplifier. At a later stage we will see that this controller could consist of complex functions like derivative of an error signal, integral of an error signal, or in general any function you could take at this particular point. But here in this configuration, in the basic structure, I assume that the controller is a simple amplifier, because the objective at this particular point is not to go to the design of the controller, but the objective is to give you the basic hardware required for a control system. So, you find that this amplifier now, this is getting two signals. One is the signal reference signal, ER is the reference signal, please see, and this ER you are able to vary by varying the position of this wiper arm. So, it means you will change the position of the wiper arm with respect to your requirement on the commanded speed. Omega r in this particular case not explicitly shown. Omega r is the commanded speed, and you want omega to follow the commanded speed omega r. So, what I am doing is, proportional to omega r, I set a signal ER, a larger omega r means a larger ER, and I can set it accordingly by setting the wiper on the potentiometer. So, this ER becomes the reference signal, and where is the feedback signal? The feedback signal in this particular case is coming from a tacho generator. Tacho generator, as you know, will generate a signal ET which is proportional to its speed. The speed being omega, so it means ET is proportional to omega. So, it means ET has got the necessary information about the controlled variable, ER has got the necessary information about the commanded value, and the difference of the two is going to give you an actuating error signal. So, this actuating error signal is being amplified, and this amplified signal, which is now becomes the control signal U, is given to the actuator, and the actuator is running the load. And the purpose of the controller design will be make suitable changes at this point, because all others are fixed components of the system. You will not like to change the motor, the tacho generator, you will rather manipulate this particular function so that omega is following the commanded value omega r. But at this point we will not go to the details of the design, rather I will like to express this diagram using a block diagram, and from there the visualization of the feedback structure and basic elements required in a system will become very clear. Okay? I may refer to this diagram again. I need your help now to set up a block diagram. What I do is I take this as the reference signal ER. This is the reference signal which is proportional to or which is a function of the commanded signal omega r. I think, if you do not mind, though the physical diagram does not have this component, let me have this component and call this component as reference input elements. Please see, physically potentiometer is taking care of this, and the reference input elements may have the signal omega r. So, omega r is the commanded position and ER is the corresponding voltage. Okay. Now, let me take an error detector in the standard block diagram. This is plus and here it is minus. You will note, I think I can go back to the diagram. You will note that ET is a minus signal, the ET plus minus over here, the ET, the suitable algebraic sign has been given to ET. So, as far as the block diagram is concerned, as far as this amplifier is concerned, you can see ER minus ET is being multiplied by the gain of this amplifier. What is the gain? It is RF by R. Is it okay please? RF by R, but with a negative sign. To take care of this negative sign, I have used an inverting amplifier with a gain of unity, so that the gain of this total amplification unit is RF by R with a positive sign. An inverting amplifier has been used over here just to take care of the sign of the gain of the amplifier, and therefore I can say that the output this error detector output ER minus ET. So, look at the unit now. What is this circle in terms of the physical system? This dotted block in terms of the physical system is your potentiometer. This circle, the so called error detector or the summing junction in terms of the physical system is an op-amp, because the op-amp is getting the two signals ER and ET is generating a signal which is proportional to the difference of the two, and the proportionality constant is RF by R. So, here I am putting in this particular block an amplifier gain RF by R, and let me say that U is this control variable. So, you will please note the physical relevance, the physical equipment also which is being used to realize the various objectives. Now, U is the control signal. This is a signal which has the knowledge about the action to be taken, but it does not have the necessary power to drive the actuator. So, you will like to add power to this signal, keeping the basic intelligence at the same level. So, what you do is you simply add here a power amplifier Ka. Ka is the gain of the amplifier. Now, this power amplifier is able to drive the motor. So, what is the transfer function of the motor? I will see, but at the time, for the time being, let me say that this block is a motor block. Suitable transfer function of the motor I am going to use over here. The output here is the controlled variable omega, okay, and this omega is being sensed by the tacho generator, which is a sensor, and let me say Kt is the constant of the sensor. So, that Et is equal to Kt into omega, and this is being fed back here. This is the basic block diagram, but for the motor block to be opened, to be detailed properly. So, I am going to give you the transfer function of the motor block, but before we go to the motor block, let me look at this block diagram with respect to the general feedback structure which was given to you. Tell me please, this diagram, this is a dotted block, this does not contain any physical component. If you look at the diagram from ER to omega and a feedback loop, it is a non-unity feedback structure. Non-unity feedback structure. It is naturally, in this particular case, there is a sensor transfer function, and this you are going to have as E cap. It is an actuating error signal, and this is a non-unity feedback structure. Now, suppose you see, as I told you, that for the purpose of analysis and design, the unity feedback structure may be more convenient. In that particular case, I will like to transform this to a unity feedback structure without sacrificing the information contained in it. So, naturally I like that the basic equation remain the same. If the basic equations remain the same, in that particular case, you please note that this Kt, this particular block should contain kT, and it has to contain kT. You please see that this kT is not a physical component there, but I will set the potentiometric constant in such a way that omega r into kT becomes the desired voltage ER, which you want to feed as the reference voltage. You will see that it is obvious that the comparison of the two voltage will give you an error signal which is proportional to the errors in speed if and only if the dotted block has got kT. I hope this point is being taken very well. This E is a voltage signal, it is not a speed signal. The unit is not radian per second, the unit is volts, but this volts will be proportional to the error in speed if and only if this block has got kT, and this is in your hand. You see, you can set the potentiometer constant. You know that the potentiometer constant is, what is the potentiometer constant? The potentiometer this voltage is equal to a constant Kp into setting of the wiper arm. So, that is a potentiometer constant. This you will design in such a way that the ER which you get, the Kp or the potentiometer constant which you get equals Kt, which is the tachometric constant, so that in that particular case the error in volts is directly proportional to the error in radian per second, the error in speed. So, therefore, the reference input elements, this is what I want to convey, may or may not be physically present in this system in the form. There is no unit like a tacho generator. Kt is the constant of the tacho generator. There is no unit like a tacho generator on the input side, but still I have a block with transfer function as Kt because it makes sense. It explains the working of the system, and this realization of the block is suitably done with by the potentiometric unit in the system. So, this becomes the reference input elements for the system, and now you see that what I am doing is the conversion of this diagram into a unity feedback system. Omega r I take, you will now tell me whether it is okay, plus minus, I club Kt here, here it is Ka, motor I have yet to explain, omega, and it goes. You can just see the two equations will remain the same, but now it should not be confused. Omega r is the reference input does not mean that physically radian per second is directly going to some unit. It does not mean that. It simply means that it is an equivalent block diagram which has got the same mathematical equation which you get from the original block diagram between omega and omega r. Now, in this particular case, this is E and not E cap, because E is the system error. E is the error between the commanded speed and the actual speed, and the cap can now be removed, and in a unity feedback system you can get E variable over here. Now, you can see that block diagram manipulation is required to help analysis and design. I claim that this type of block diagram, when we go for analysis and design, is going to be more convenient. Okay? So, a non-unity feedback system has been appropriately converted to a unity feedback system for the purpose of further usage of this particular block diagram. I hope this is okay. Now, let me come to the motor, because the block diagram is not yet complete. If I come to the motor, this motor used in this particular control system has got this configuration. In this case, the armature voltage is EA, okay, and RA is the armature resistance, IA is the current through the armature, and here is the motor shaft, and I have a load here. Okay. The motor produces a torque Tm and the load disturbance torque is Tw. The parameters of the load are J and B, and let us say the speed at which the motor runs is omega. I want you to give me the mathematical model of this system, so that the motor block in the diagrams we have used could be replaced by that block diagram model or the transfer function model of the motor. The things are known to you. Well, I will simply revise the basic relationships for you. Let me look at the armature circuit. EA is the applied armature voltage and EB is going to be the back EMF. Okay? You will see that I have neglected the armature inductance. In a simplified model, this is usually okay. I mean, as far as the characteristics of the motor is concerned, this armature controlled motor is concerned, that the inductance can be neglected. So, in that particular case, the basic equation becomes IA equal to EA minus EB divided by RA. This is equation 1 I get for the motor model. Okay. Now, this IA, you will note that IF, the field current, is constant and IA depends upon the applied voltage. However, the torque produced by the motor, as you know, is proportional to the product of the two fluxes and hence the two currents. Since IF is constant, I can say that the torque produced by the motor is proportional to the armature current, IF being constant. So, I now write Tm is equal to Kt into Ia, where Kt is the torque constant of the motor. The point may be please be noted, Kt is the torque constant of the motor, and this has come this way because If, the field current, is constant and it is an armature controlled motor. That is why the name is given, because you are controlling the armature current through IEA and the field current is held constant. The speed of the motor is being controlled by controlling the current through the armature. What other equations will come? What is the value of EB, please? This is equation number 2. EB I can take as proportional to speed, of course, and therefore I take a proportionality constant Kb, which is the back EMF constant. Proportionality constant Kb into omega, omega is the speed in radians per second, and this is your equation number 3. And now this torque Tm, what is this torque doing? This torque is driving the load. So, write is in equation the force balance, the torque balance equation over here. In that case, I can write Tm is equal to J omega dot plus B omega plus Tw. This is your number 4. Tw is the disturbance torque, J omega dot is the inertial torque opposing the motion, B omega is the frictional torque opposing the motion. So, the torque applied by the motor is equal to all the terms opposing the motion. So, this becomes the basic equation. Come on, please help me now. I want you to give me these 4 equations in terms of a block diagram. This, because as I said that manipulation in terms of block diagram will become more convenient for us in terms of the block diagram, and we can avoid writing these equations in Laplace domain. You can directly give me, you see, I think now you should be equipped with the required tools that the manipulation can be done directly. So, what do I do? EA is your input signal, this is the input signal. So, let me get started with the input signal. This is EA. In Laplace domain I can write this as EAS, S I am not writing to save space. Now, this input signal, you find the back EMF signal coming over here plus minus. So, this is EB. The difference of the two divided by 1 by RA is your armature current IA. Please follow up the equations, and once we have done it, you see that for later applications you will be able to write the block diagram directly without explicitly writing the equations. IA you have got, multiply it by the torque constant, you have got Kt. Can you help me here? What should I do to proceed further? Now, I have got the torque produced by the motor, it is IA into Kt. Now, what is the net torque which is available for driving the inertia? It is not Tm, it is Tm minus Tw. Tw may oppose or help, I do not know, but you see the net torque is the algebraic sum of Tm and Tw. So, in that particular case I can use a summing point here. I can say that plus and here it is Tw minus. So, the net torque available for driving the inertia is Tm minus Tw. I think it's, I hope it's okay. And now this torque since this is driving the inertia, this particular block could be 1 over Js plus B with output as omega. You can see the basic relationships. This omega now can be picked up by the sensor, and here is your sensor transfer function kT, and this is I am sorry, there is no sensor here. This is the transfer function of a motor only in the open loop mode. There is no sensor in as far as the motor is concerned. This is actually Kb, the back EMF. This feedback link, please see, is not being provided by any sensor. It is inherent in the structure of the motor, in the motor operation. Kb is the back EMF. So, Kb into omega is your back EMF, and here gets the loop completed. So, you please note there is a feedback loop, though if you look at the motor, you have not installed any sensor to give the feedback signal. This is an inherent feedback loop in the motor, and this rather is an important characteristics of the armature controlled motor. You will see that when I take the field controlled mode, the inherent feedback loop is not there, and many a times this particular inherent characteristics of the armature controlled motor is a useful characteristic because it provides the required damping. This I will show later. So, this becomes the block diagram structure. So, let me now put it in a more convenient form, which I will be using quite often. EA does not matter, I can put the variables in this form as well, plus minus Kt by Ra plus minus Tw 1 over Js plus B omega Kb. Please see that this is the block diagram model for the motor, and I can place this model in the overall system model to get the close the block diagram model for the speed control system under consideration. Before I go to that, let me study the characteristics of this motor. Please see, if I set the disturbance 0, I get the transfer function between omega and Ea. I need your help here. Omega s over Eas is equal to Kt by Ra divided by Js plus B over 1 plus Kt Kb by Ra divided by Js plus B. This becomes the transfer function model between omega and Ea. Please simplify this. If I simplify this model, I get this as equal to Kt divided by Kt by Ra, let me take it here, Js plus B plus Kt Kb by Ra. This is your transfer function model for the motor. Now, in terms of the time constant, could you give me the transfer function model for the motor in terms of time constant? I will like to write this as omega s over Eas is equal to Km, the motor gain, let me call it, divided by tau ms plus 1. It is a first order transfer function model, and tau m can be suitably written. Please see, tau m will become j divided by this total unit. J divided by this total unit is your tau m, and this function divided by this total unit, this total term becomes your system gain or the motor gain constant Km. So, the motor transfer function between the output omega and the input Ea is a first order transfer function Km over tau ms plus 1. Please store it in your memory, I will be requiring this information quite often. Now, I want your comment on the effect of Kb, the inherent damping characteristics of the motor. You will please note that Kb increases the value B, and hence it increases the effective damping of the motor. So, it means it is because of Kb the oscillations of the system can be quickly damped out, the feature which will not be available, as you will see when we come to the field controlled mode. Equivalently, in the time constant form, what happens to the time constant because of Kb? does it increase or decrease? The time constant because of kb, it decreases, and as you know, smaller the time constant, faster is the response. Okay. So, quick damping means the oscillations are damped out quickly and the motor comes to the steady value quickly, and this is the characteristics of this inherent loop which is there in an armature controlled motor. I hope this is okay. So, now let us go back to the original system wherein I have to place the motor and give you the overall transfer function of this overall block diagram of the system. I can take up the unity feedback system. If you understand this very well now, omega r is the input I am taking. I know that physically it is ER which is being given as the input, but in the block diagram for the purpose of analysis and design I could take omega r as the input, plus minus here KT RF by RA is the gain here, KT small t, the tachometric constant. This is your EA, this is your EA, the voltage. Please see, this is the voltage available from the amplifier. This voltage is going to the power, this is not EA, this is going to power amplifier, this is U signal. I am sorry here at this point, this is U signal. The power amplifier output is EA, the voltage which is going to the armature controlled motor. Now, I will like to put the summing junction here, because at this particular EA you have got EB, the back EMF of the motor. Now, this has a block KT over RA here, so that at this particular point you have got the torque. This is the torque generated by the motor. Put another summing junction with a negative sign here. This is your TW, the disturbance torque on the motor. Yes. This torque is available for driving the inertia. So, this is 1 over Js plus B. This is omega the speed. From omega I take a loop to generate the back EMF signal. From omega I take another loop, it is a multi loop configuration now through the sensor KT, so that it is going to this particular summing junction and is giving you the primary feedback loop. I will put the diagram this way, KT is going to the summing junction, base this summing junction, and is going giving you the primary feedback loop, and this becomes, oh I am sorry, KT has been taken over there, it is a unity feedback system, you are very right. It is a unity feedback block diagram now, KT has been taken in the forward loop. So, as far as this diagram is concerned, it will go through unity. So, this becomes the total speed control system block diagram. The design and analysis aspects will come later. Now, you know the block diagram reduction tools. Since the block diagram reduction tools are known to you, using those tools either through signal flow graphs or directly, you can get me the transfer function between omega and omega r. You can get the transfer function between omega and TW, it depends upon the interest you have. If you want to study, if you want to analyze the system with respect to the commanded position, get the transfer function between, or in general omega s is equal to ms omega rs plus mws TWS could be obtained by block diagram reduction. That is why the reduction methods, Mason's gains formula and direct methods were given to you, because these will be subsequently required. And I leave this as an exercise to you, that for this particular block diagram get me an equation of this form which gives you an output variable in terms of the commanded speed and the disturbance signal. It is a 2 input 1 output system. Okay. Fine. One more diagram I wanted to take, and that is a position control system. Once you have got the speed control system very clearly, there will not be any problem here, it will follow very easily. See the objective of this function, this system, and how does it work. In this particular case again, I have a reference input ER in terms of voltage. and this reference input is the commanded position. I want to command the position of the load, it is a position control system now, in contrast to the earlier system which was a speed control system. So now ER, again summing junction is the two voltages, but the meaning of the two voltages has become different. This ER is a signal which represents the desired position, and this desired position can be set on the potentiometer, so that ER is equal to Kp into theta r, where Kp is the potentiometric constant. Okay? I hope you get it. Now let me see the feedback signal at this stage. Feedback signal is this particular load position theta L. This load position theta L could also be converted into a voltage signal by a potentiometer. Now I will like to take the potentiometric constant identical. Please note that this assumption will make it possible to convert the block diagram of the overall system into a unity feedback block diagram. If that is not there, you will not be able to get a unity feedback block diagram, and there is no problem in taking two identical potentiometers with the same potentiometric constant. So ER here is Kp into theta r, let me call this E naught. So E naught here is Kp into theta L, where theta L is the load position, it is the controlled position which is required to follow the commanded position theta r. Okay. So see the variables please, theta r and theta L are the two variables, and you will take note the sign. The sign I have inverted, minus plus and minus plus taken this way. You will please note the wiper on the potentiometers have been taken in this way, that at this particular point the input of the op amp is ER minus ET, input to the op amp, ER minus E naught, where E naught is the output voltage of the potentiometer. This you can see with respect to this potentiometer wiper R movement. Okay. Now this voltage ER minus E naught is being amplified. So it means the error detector, this particular amplifier is an error detector which gives you a voltage proportional to the difference of the two. Here again I have an inverting amplifier, so that the minus sign is taken care of. I have an power amplifier over here, so that the motor, this particular signal is to drive the motor. This motor produces the torque, and this particular torque is required to drive the load. Now a point to be noted, that I have not coupled the load directly to the motor shaft. I need your attention here. I have not coupled the load directly to the motor shaft. The reason being that many a times for the movement of the load, I need the speed reduction and the torque magnification. You will find that this particular gear set, let me call it, this is set of two gears, there may be a set of more gears. So let me call this as a gear train. A set of gears suitably connected, suitably installed is a gear train. This gear train is providing the required amount of torque magnification. If the torque required at this particular, the torque generated at this particular point is lower than the torque required at this particular point, the load is heavier. In that particular case you will like to magnify the torque, and this particular gear train is giving you the torque magnification. We are going to derive the model for the gear train, therefrom you will find that a suitable torque magnification is possible, and in the process speed reduction will take place, that is theta m dot and theta L dot, and torque ratio will be in such a way that the gear train reduces the speed and magnifies the torque. The objective becomes very clear, it is as per the load requirements you will install a suitable gear train. So after that, this is the load position, this is the motor position, the load position is being sensed and is being fed back. I hope the basic configuration of a position control system becomes clear, and the transfer function of each and every model will is clear except for the gear train, which I have to explain. So now let me look at the gear train first, so that the complete block diagram could be obtained. A set of two gears I am taking. If the gears are more than two, accordingly you can generate a suitable transfer function model for the gear train. Let us say that Tm is the torque generated here, the motor torque, theta m is the position, N1 number of teeth on this gear, N2 number of teeth on this gear, and here is a load. Naturally the reversal in direction will take place. So naturally I am writing theta L this way, and this drive torque is going to drive the load in this direction. So if I want to show a disturbance, I must show a disturbance this way, because the drive torque on this particular load is coming this way. So this is your disturbance Tw. Help me to derive a suitable expression giving you the relationship between Tm and the torque here and the speed here and the speed there. I want a suitable relationship for that. Well, it follows this way. I take R1 as the radius of this gear, R2 as the radius of this gear. You will note that the number of revolution of the two gears will be different, because the linear distance travelled by the two gears has to be the same. Okay? Therefore, I can write theta m R1 is equal to theta L R2. I hope this point is well taken. Theta m R1 has to be equal to theta L R2, because the linear distance travelled has to be the same. Assuming that R1 and N1 are proportional, naturally they will be. R2 and N2 are proportional. In that particular case, I am writing N1 by N2 equal to theta L by theta m. This I term as my first basic equation. N1 by N2 is the teeth ratio, and theta L by theta m is the ratio of the two positions. And you won't mind if I put it this way, that this is equal to theta L dot by theta m dot as well. That is the ratio of the two velocities, because you can take the derivative of this equation and you can arrive at this particular expression. If you take the derivative of this equation, N1 by N2 is equal to theta L by theta m is equal to theta L dot by theta m dot is the expression you get, which gives you the ratio of the two positions or two velocities as equal to the teeth ratio, the gear ratio it is called. N1 by N2, let me say, is the gear ratio n, small n. Okay. Now look at the torque expression. Now you see Tm is the torque generated by the motor. Okay. Now let me assume that the torque transmitted to this particular shaft is T21. T21 is the torque transmitted through the gear train onto the load shaft. So T21 is responsible for driving the inertia against the disturbance Tw. You see this point, T21 is responsible for driving the inertia against the disturbance Tw. How about the gear 1? Please see that if I remove gear 2, the total load torque on gear 1 will be less compared to the situation when gear 2 is present. It means as far as the motor shaft is concerned, the gear 2 and the load is loading the motor shaft. Just look at the motor shaft only. The motor shaft is being loaded. You can see the two situations. Without the gear 2 and with the gear 2, the situation on the motor shaft becomes different. And let me say that the total load provided on the motor shaft by the gear, by this particular load and the gear, is T12. So I put it again, T12 is the loading of the motor shaft due to the load and the gear, the secondary gear or gear 2, and T21 is the drive torque transmitted to the load shaft by the motor shaft. So in this case, if I want a relationship between the two, I know that at this point of contact the forces developed should be the same, they cannot be different, and therefore I write a relationship T12 by R1 is equal to T21 by R2, because the force developed at that particular point is T12 by R1, and the force developed, if you look at T21, it is T21 by R2, and this gives me the relationship T12 is divided by T21 is equal to N1 by N2. that is the ratio of the two torques is equal to the gear ratio. This point needs your attention, please see. N1 by N2 is the gear ratio, and this provides this T12 by T21 is the ratio of the two, is equal to the gear ratio. And now look at the point I made, that the gear train magnifies the torque and it reduces the speed provided your N is less than 1, and N as per the gear train shown over here will be less than 1 because N1 is smaller than N2. Typically N could be 1 by 30, let us say. Typical value you take N is equal to small n is equal to 1 by 30. If you take 1 by 30, you find theta L dot is equal to 1 by 30 into theta m dot. It means the load speed has reduced by a factor equal to the gear ratio. T21 equal to T21, now you take in this T12 is 1 by 30, so T21 is equal to 30 into T12. The torque available at the load shaft has been increased by a factor of 30, which is inverse of the value n, the gear ratio you result. So it means the gear train here provides the required torque magnification and corresponding speed reduction, and how do you fix up the gear ratio naturally depends upon the characteristics of the motor and the load. These two units will dictate the value of the gear ratio, and accordingly you will design a suitable gear ratio for the system. Okay. Now let me come to the equations. Please see, here is a motor. This is the load here. Come on, give me the equation at the motor shaft. I assume that this particular motor itself has got certain moment of inertia Jm and viscous friction Bm. The motor itself has got moment of inertia Jm, or let us neglect it for the time being. Tm is the torque developed by the motor. I take it this way. Let us say Jl is the moment of inertia here and Bl is the viscous friction and Tw is the load torque. I need your attention here, please. I am now setting up the equations. Please set up the equation for the secondary term. For the secondary term, the equation becomes T12 for the secondary gear and the load. T12 is the torque transmitted by the motor. This is equal to JL theta L double dot plus BL theta L dot plus TW. This becomes the equation at the load shaft. Please give me the equation at the motor shaft. What is the applied torque? Tm equal to, yes, we said that the opposition due to the secondary gear and the load on the motor shaft is represented by T12. Okay, let me at this stage itself make the discussion complete. Jm and Bm could be taken as moment of inertia and viscous friction of the motor shaft. There is a friction in bearings of the motor shaft. There may be friction in this part of the system which has been captured into a coefficient Bm. Help me please, give me the equation for the motor shaft. Tm is the developed torque, theta m is the angular displacement of the motor shaft. In that particular case, Tm is equal to Jm theta m double dot plus Bm theta m dot plus T12. Okay. Now you see that what I want to do is I want to eliminate the variables T21 and T12. Help me in that. If I want to do that, let me retain these equations here. Eliminating the variables T1 to T21 and T12, I can write the expression as a very important expression I am going to give you at this stage. Tm is equal to Jm theta m double dot plus Bm theta m dot plus what is T12? T12, if you recall, is nothing but N1 by N2 into T21. Okay. So if you want to replace this expression, I can write this as N1 by N2 into T21, which could be written as JL theta L double dot plus BL theta L dot plus TW. These variables T21 and T12 have been eliminated. Now you see one more point, that the variables theta L and theta M are not independent, they are related by a constant. So your equation having both the variables theta M and theta L is not logical. Your equation should have one of these variables, either theta M or theta L, and mostly the basic equation is written in terms of theta M. So I want you to eliminate theta L as well. Come on, please get started. You eliminate this and I also do it and then compare the result. Let me write it this way. I want to eliminate theta L and write the basic equation. This becomes Tm equal to Jm theta M double dot plus Bm theta M dot plus N1 by N2 squared JL theta M double dot plus N1 by N2 squared BL theta M dot plus N1 by N2 into TW. You will see this equation, please. Theta L dot and theta L have been replaced as equal in terms of theta M. You know the expression, theta L by theta M is equal to theta L dot by theta M dot is equal to the gear ratio N1 by N2. So you see the interesting interpretation of this equation is the following. I can club these terms corresponding to theta M dot, Jm plus this term, Jm plus this term I am going to get as the total inertia term. I can club these two terms, Bm plus this term I am going to get as the total frictional term, and this is the equivalent disturbance on the load, and hence the expression Tm is equal to Jm plus N1 by N2 squared JL into theta M double dot plus Bm plus N1 by N2 whole squared BL, sorry, yes, this is okay, theta M dot plus N1 by N2 TW. Please see what is the interpretation of this. The interpretation of this particular equation is this, that mathematically, you see you have been simplifying the block diagrams. Here also let us do some simplification. Mathematically your system which we have described as position control system is equivalent to the following situation: a motor, this is load, forget about the gear train altogether. You assume that a particular load is there directly on this particular motor. What are the parameters of this particular load? The parameters of this particular load are J equivalent. What is the value of J equivalent? You will find that J equivalent is given by this expression, J equivalent, and you can take the load on this particular motor to be equal to B equivalent, which is given by this particular expression. And what is the disturbance directly coming on the motor shaft? Actually, physically speaking, the disturbance is coming on the load shaft, but if you take the disturbance as N into TW, where N is the gear ratio is equal to N1 by N2, this becomes the representation. And why did we take this representation? Because writing the mathematical equation for this representation becomes simple. So with this representation for the motor shaft, now the situation of the overall control system which we have taken becomes identical to the situation we have handled for speed control system, and I leave this as a simple exercise for you to give me the block diagram of the system, or well, I know the time limit, but just let me quickly give you the block diagram and that is the end. Theta r is the reference input, this is your Kp which you can take inside, Er is this voltage, plus minus this is E naught the feedback, this is being compared Rf by R into Kt Rf by R gives you U here, the control signal. What is this control signal doing? This control signal multiplied by Ka gives you Ea. Okay, let me save time over here and I put the motor here. The complete block diagram of the motor could be put over here at this particular point. What is the output of the motor? Output of the motor in this case is motor speed omega. Motor speed omega into 1 by S, an integrator, gives you position theta m. Okay. This position theta m from this particular point, now I think you can connect the block diagram, you can convert it to theta L, take a suitable feedback loop through the output potentiometer and the inherent loop on the back EMF also will come. I leave this as an exercise for you to complete the block diagram for the system. There is a pressure of time. Thank you very much.